Swayam Prabha. Digital India. Educated India.
Dear viewers, today I will discuss another technique of photogrammetry known as terrestrial photogrammetry. Terrestrial photogrammetry is an important branch of the science of photogrammetry. It deals with the photographs taken with the cameras located on the surface of the earth. The cameras may be handheld, mounted on tripods or suspended from towers or other specially designed mounts. The term close range photogrammetry is generally used for terrestrial photographs having object distances up to 300 meters. Unlike aerial photographs, with terrestrial photography, the cameras are usually accessible so that direct measurements can be made to obtain exposure station positions. Camera angular orientation can also usually be measured or set to fixed values, so that all elements of exterior orientation of a terrestrial photograph are commonly known and need not be calculated. These known exterior orientation parameters are source of control for terrestrial photographs, replacing in whole or in part the necessity for locating the control point in the object space. Terrestrial photography may be static, that is for stationary objects, or dynamic for moving objects. For static photography, slow, fine grained, high resolution films may be used and the pictures taken with long exposure times. Stereo pairs can be obtained by using a single camera and making exposures at both ends of a baseline. In taking dynamic terrestrial photographs, fast films and rapid shutter speeds are necessary. If stereo pairs of dynamic occurrences are required, two cameras located at the ends of a baseline must make simultaneous exposures. Before I discuss the concept of terrestrial photogrammetry, let us look at what are the application areas, so that we will be able to appreciate the technology of terrestrial photogrammetry. Historically, the sciences of photogrammetry had its beginning with terrestrial photograph, and topographic mapping was among its early application. Terrestrial photos were found specially useful for mapping rugged terrain, which was difficult to map by conventional field surveying methods. Although it was known that topographic mapping could be done more conveniently using aerial photographs, no practical method was available for taking aerial photographs until the airplane was invented. Following the invention of the airplane, emphasis in topographic mapping shifted from terrestrial to aerial methods. Terrestrial photogrammetry is still used in topographic mapping, but its application is usually limited to a small area and special situations such as deep gorges or rugged mountains that are difficult to map from aerial photography. Other topographic application of terrestrial photogrammetry are in mapping construction sites, areas of excavation, borrow pits, material stockpiles, etc. Through the years, terrestrial photogrammetry has continued to gain prominence in numerous diversified non-topographic applications. So, now let us look at which are the non-topographic applications by virtue of which terrestrial photographs can be used. These are agriculture, conservation ecology, forestry, archaeology, anthropology, architecture, geology, geography, engineering, mining industry, criminology, oceanography, medicine, dentistry, and many more. In the field of medicine, X-ray photogrammetry has been utilized advantageously for measuring size and shapes of body parts, recording tumor growth, studying the development of fetuses, locating foreign objects within the body, etc. Terrestrial photogrammetry has been used to great advantage as a reliable means of investigating traffic accidents. Photos which provide all information necessary to reconstruct the accident may be rapidly obtained. Time consuming sketches and ground measurements, which all too often are erroneous, are not needed, and normal traffic flow can more quickly be restored. Terrestrial photogrammetry has been widely practiced in accident investigations for many years in several European countries. Time-lapse terrestrial photographs have been used to record speeds of automobiles, directions and velocities of water currents, rate and manner of plant growth, etc. A unique and highly specialized application of terrestrial photogrammetry was in connection with the establishment of a worldwide satellite triangulation network. In this program, positions of orbiting satellites were recorded as they passed through the field of view of highly precise ballistic cameras. The camera stations, which usually serve as a framework for a worldwide geodetic datum, were widely distributed and their positions accurately determined on the basis of measurements taken from the photographs. In the space program, terrestrial photos are used to calibrate large parabolic antennas used in tracking spacecrafts. Terrestrial photogrammetry has become a very useful tool in many areas of scientific and engineering research for several reasons. One reason is that it makes possible measurements of objects which are inaccessible for direct measurement. Also, measurements can be obtained without actually touching delicate objects. In some experiments, such as measurements of water and currents, physical contact during measurement would upset the experiment and render it inaccurate. Cameras which freeze the action at a particular instant of time make possible measurements of dynamic occurrences such as deflection of beams under impact loads. Due to the many advantages and conveniences offered by terrestrial photogrammetry, its importance in the future seems assured. Having discussed the applications, now let us look at how the terrestrial photographs are acquired, These cameras which acquire terrestrial photographs are known as terrestrial cameras. A variety of cameras are used in terrestrial photography. All of them fall into one of the two general classifications, that is metric or non-metric. The term metric camera as used herein includes those cameras manufactured expressly for photogrammetry application. They have fiducial marks built into their focal plane, which enable accurate recovery of their principal points. Metric cameras are stably constructed and completely calibrated before use. The calibrated values of focal length, principal point coordinates and lens distortions can be used with confidence for long period of time. Non-metric cameras are manufactured for amateur or professional photography, where pictorial quality is important, but geometric accuracy requirements are generally not considered paramount. These cameras do not contain fiducial marks, but they can be modified to include them. Non-metric cameras can be calibrated and used with satisfactory results for many terrestrial photogrammetric applications. Aerial cameras can be used for terrestrial applications, but this requires special tripod mounts. Aerial cameras used for terrestrial photography would of course be considered as metric cameras because of their stability and calibration characteristics. Most metric terrestrial cameras are fixed for focus at infinity and cannot produce sharp geometrically correct images at very short ranges. These cameras can be modified, however, to permit sharp focus at short ranges. Of the many available terrestrial cameras, only a few are described and pictured herein as examples. Exposures with metric cameras are often made directly on glass plates. Therefore, film flattening devices are not necessary and the utmost in dimensional stability of the images is achieved. Many metric cameras use polyester based films having high dimensional stability. Phototheodolites and stereometric cameras are two special types of terrestrial camera systems in the metric classification, which are described in the following two sections. Omissions of other comparable cameras is not intended to imply any inferiority of these instruments. Phototheodolite. The term phototheodolite generally applied to a combination of camera and theodolite. In a broader sense, however, a phototheodolite is any camera, usually metric, equipped for orienting its optical axis in a known direction with respect to baseline. Phototheodolites are generally mounted on tripods and centered over a desired camera station by means of a plumb bob. The Zeiss TMK is a terrestrial camera of the phototheodolite classification. The picture at the side shows a typical layout of a Zeiss TMK phototheodolite. It has a telescope with crosshairs for sighting along a baseline, and by means of a right angle prism, the camera axes may be oriented at 90 degrees to a baseline. If the camera optical axis is directed at 90 degrees from both the ends of a baseline, as shown in the next figure, the photographs of the resulting stereo pair have their optical axes parallel. So, in this particular diagram we can see that the optical axes of the phototheodolite have been kept perpendicular to the baseline, and the hatched area as a matter of fact provides stereoscopic vision or measurements can be undertaken in this particular region. The TMK phototheodolite has a normal focal length of 60 mm and its pictures are exposed on glass plates of dimension 90 by 120 mm. The next phototheodolite is the Wild P30, which fits the classical description of a phototheodolite. It combines a Wild T2 theodolite and a metric camera, as can be seen in the picture besides. The theodolite has an upper and lower motion. With its upper motion locked and the lower motion open, the camera and the theodolite turn azimuth as a unit. With the upper motion open and the lower motion locked, the theodolite can be turned in azimuth while the camera retains its direction. Now, let us look at stereometric cameras. A stereometric camera consists of two identical metric cameras mounted rigidly at the ends of a fixed base, so that their optical axes are parallel to one another. This means that relative orientation of the camera is known after calibration, and it remains constant for all stereo pairs taken. The shutters of both cameras are actuated simultaneously, a condition enabling dynamic recurrences to be photographed stereoscopically. A variety of stereometric cameras are available, affording a wide choice in the field of view, format, dimensions, focusing distances and fixed base lengths. The lengths of the fixed base may vary with different cameras, but 200, 120 and 40 centimeter lengths are common. Shorter base systems apply for photographing at close range. This particular slide shows the layout of a Zeiss SMK stereometric cameras consisting of two TMK cameras mounted at a fixed base of 120 centimeter. Having now looked at the various types of devices which can be used for acquiring terrestrial photographs, now let us proceed and look at how after the photographs have been acquired by these cameras, what sort of measurements can be made. So, the first measurement which is of importance is to find out the spatial coordinates, that is x, y and z. So, let us look at how these can be derived, because we need to make certain observations which could be angular in nature. So, we now discuss the horizontal and vertical angle measurement. A horizontal terrestrial photo is obtained if the camera axis is horizontal when the exposure is made. Two planes of a horizontal photo is then vertical, and if the camera is properly leveled before exposure, the x and the y photo axes defined by the fiducial lines are horizontal and vertical lines respectively. The figure below shows the positive of a horizontal terrestrial photograph exposed at a camera station L. The focal length of the camera is f and O is the photographic principal point. Points A and B in the object space are imaged as small a and small b, and their photo coordinates are x a, y a, x b, y b respectively. we would like to find out what is the horizontal angle between the camera axis and the point A which is there. So, if we see here, the horizontal angle, as a matter of fact, is the angle which is being made by the point with respect to the photo center of the terrestrial photograph at the exposure station. So, let this be the horizontal angle for point A be alpha A between the optical axis L O and the ray to the object point A, and this can be expressed as alpha is equal to tan inverse x A divided by f, where x A is the photo coordinate of point A in the x direction and f is the focal length of the camera. Also, the vertical angle of inclination of point A with respect to the vertical plane and the ray to the point A can be expressed as beta A, which is equal to tan inverse y A divided by the square root of the square of x A square plus y plus f square. In the similar manner, the horizontal and vertical angles of point B can be determined, where alpha B will be equal to tan inverse x B divided by f and beta B will be equal to tan inverse y B divided by the square root of the square of x square plus f square. So, the horizontal angle between A and B at the camera exposure station L can be designated as h small a small h L B small h subtended at the exposure station by the two objects is alpha A minus alpha B. The horizontal and vertical angles determined by the above equations are the same angles that would be measured using a surveyor at the camera station. An advantage of the photographic approach is that one click of the shutter instantaneously produces an infinite number of points to which angles may later be determined. The photo measurements may be made in the comfort of an office. An important consideration, if the alternative requires field surveying during times of adverse weather. Now, let us look at how to locate points by intersection from two or more horizontal photos. If the images of an object point appear in two or more horizontal photographs, the position and the elevation of the point can readily be determined, provided the camera positions and the directions of the optical axes are known. The figure illustrates two horizontal photographs taken from exposure station L and L dash. In this figure, there are one is figure A, it shows the locations of the intersection from two horizontal terrestrial photograph. The cameras are placed at the station L and L dash and the photograph has been taken of a point A. With respect to the first station L, the height of the point A with respect to the horizontal plane defined by the camera axis is V A, whereas with respect to the second station L dash, the height of the point with respect to the horizontal direction plane is V A dash. Similarly, the vertical angle is beta A dash and beta A for the point A, and in order to find out the coordinates, we normally try to create a local coordinate system with its origin located at the position L, and with respect to that we find out what is the ground coordinates of that particular point A with respect to the first camera location L. Figure B is a plan view of the situation. Image of object point A appear at A and A dash on the two photographs. Assume also that the horizontal length of the baseline has been measured and that the camera station elevations are known. An arbitrary x y object space coordinate system is adopted with origin at the exposure station L and the x axis in the plane of the baseline. It is required to determine the x and y coordinates and the elevation of point A. This problem may be solved analytically or graphically. In the analytical solution, the angles alpha A, alpha dash A, alpha A dash and beta A dash are calculated from equations 1 and 2 determined previously. Then the angles phi, phi dash and phi double dash are calculated as follows, where phi is equal to delta minus x A alpha A, phi dash is equal to delta dash plus alpha A dash, phi 2 dash is equal to 180 degrees minus phi dash. Now, by applying the laws of sine, distance L A may be calculated as B multiplied by sine phi dash divided by sine phi double dash. Also by the law of sines, L dash A is equal to B sine phi divided by sine phi double dash. So, the coordinates of x A and y A may then be calculated as x A is equal to L A cos phi, y A is equal to L A sin phi. A check on these coordinates may be obtained as follows, that is x A is equal to B minus L A cos phi dash and y A is equal to L dash A sin phi dash. The elevation of the point A is determined as elevation of A is equal to elevation of L plus V A, where V A is equal to L A H tan beta A and L A H is equal to the horizontal length L A. A check may also be obtained on the elevation of A as follows, where V A dash is equal to L dash A dash H tan beta A dash and L dash A dash H is equal to the horizontal length L dash A. If the images of an object point appear on more than 2 photos, additional check values on the position and elevation may be obtained and the average of several solutions can be adopted. Now, let us look at how do we determine the parallax equations. If a stereo pair of horizontal terrestrial photo is exposed with 2 camera axes perpendicular to the baseline, parallax equations similar to equation 5 through 8 for vertical aerial photos may be developed for calculating positions and elevations of points in the overlap area. Here, 2 cases must be considered in the terrestrial situation. First, where the exposure cameras have equal elevations, and second, where they have unequal elevations. So, let us look at the first case where equal elevations of camera stations is considered. The figure illustrates a stereo pair of horizontal photographs exposed at camera stations L and L dash having the same elevations. An arbitrary x, y, z object space coordinate system is adopted with origin at exposure station L. The y axis is horizontal and coincident with the optical axis of the left photo, x is horizontal and coincides with the baseline and z point is vertically upwards. Object point A appears in the overlap area of the stereo pair. If photo coordinates measured with respect to the fiducial axis systems are x a and y a on the left photograph and x dash a and y dash a on the right photograph, the parallax equations for calculating the object space coordinates x a, y a and z a may be developed by equating similar triangles of LOM and capital LOM, from where we get x a over y a is equal to x a over f, or x a is equal to x a over f multiplied by y a. Similarly, b minus x a divided by y a is equal to minus x dash a over f, or x a is equal to b plus x dash a divided by f multiplied by capital Y a. Equating a and b and substituting p a as x a minus x a dash and reducing, we get y a is equal to b into f divided by p a, and now substituting this value in equation into the equation a, x a capital X a is equal to b multiplied by x a divided by p a, and similarly we can find out what is the value of z a, which is equal to b y a divided by p a. Now, let us look at the second condition wherein it is equal elevations of camera station. In many situations, because of terrain variation, equal camera heights are impossible. A stereo pair taken with unequal camera heights is shown in the figure. Even though the cameras are not at equal elevations, if the photos are horizontal and exposed with their optical axis parallel, parallax equation 13 through 15 may still be used. Like the case of an equal camera height, the object space coordinate system has its origin at the left exposure station. As shown in the figure, the y axis is coincident with the optical axis of the left exposure, x is horizontal and in the vertical plane containing the baseline, and z points vertically upward. Equations 13 through 15 may be used without modifications for horizontal stereo pair taken with unequal camera locations. Parallax and photo coordinates, however, must be calculated with respect to the fiducial axis systems. These are not true parallaxes, but rather projections of the true parallaxes on the axis. If a parallax bar is used for parallax measurement, the photos must be oriented as shown. The line joining the principal point and the conjugate principal point make an angle xi which is the inclination of the baseline L dash with the horizontal, and may either be scaled from the photos or calculated as xi is equal to tan inverse delta h divided by b, wherein in this equation it is the difference in elevation of the two exposure stations and b is the horizontal distance between them. With this approach, the elevation and ground coordinates of any point can now be determined. In my next session, I would now like to introduce to you the utility of digital elevation model, or in short known as DEM. Thank you.